So we were discussing this transform, which was very similar to the Cauchy transform, which was defined like this. Right? So it only differs by the Cauchy transform by some constant. This depends on the function, right? This part here doesn't depend on z. So when we differentiate with respect to z, all the identities we know hold true if we differentiate from the outside. So if we do d by dz bar of p of f, we're going to get back to just f. And if we do z of f, we will end up with the Bernoulli transform, right? And we spent all of Friday proving the following LP bound on this thing, that if f belongs to LP, complex plane, and p is bigger than 2, then actually we'll have that, take the sup norm of this thing. If we take this thing acting on z itself, then it's less than some fixed constant times the LP norm of f times z of 1 over 2 minus p. Right? That's what we established. Yeah? Cool. So, claim. P maps LP into Holder space. C of 0, 1 over 2 over p, like this. Okay? Not sure if that's the way I should write it. i.e., if we have p of f of z1 minus p of f of z2, it is less than the same constant, the LP norm of f, and then z1 minus z2. The 1 over 2 over p, which will be something that we will use shortly. So, why is this the case? So, proof. Well, let's just look at this expression right here. So, let's look at this internal expression inside this brackets. Let's call this thing star. From up here, we see that there's going to be this cancellation of this part right here, right? So, what we'll have is that star will be equal to minus 1 over pi, a double integral over the complex plane. And we're going to have f of zeta minus z1 minus f of zeta minus z2, d zeta, like this. Yeah? Because again, this thing is just, doesn't care what z is. This part is just a constant depending on f, so it vanishes. Yeah? So, let's make a rearrangement of this. Let's define w to be equal to zeta minus z2, like this. Yeah? So in particular, that means that zeta equals w plus z2. And let's make the change of variable and integrate with respect to w. Since it's over the entire complex plane, the domain remains the same. So it's minus 1 over pi, this. And then this guy right here will now become f of w plus z2. On the bottom here, we're going to have w plus z1 minus z2. Oh, sorry, plus z2 minus z1. Like this, right? And in here, we're going to have f of w plus z2 and this thing is just going to be over W, dW. Yeah? And then define G of W to be equal to just F of W plus Z2. So this is just shifting F, so then the L2 norm of G of the entire complex plane, or LP norm, is the same as the LP norm of F, right? And then this expression now is exactly minus 1 over pi, this thing, and here we can have G of W, and let's write that as W minus Z1 minus Z2, like this. And then minus G of W over W. And that's exactly the same as this operator P acting on G at the point Z1 minus Z2. Yeah? Thumbs up if you agree with me. Cool. So, if we take the LP norm of this expression, so let's write it like this. Then this is, well, it's actually equal to, by equalities we've just had, this is equal to the LP norm of G, stop. Let's go back. Concentration vanished for a second. Let's do that again. If we take the absolute value of this expression right here, so absolute value of star, like this, then by this set of inequalities, or set of equalities, this is the absolute value of the operator P of G acting on Z1 minus Z2, because these are all equalities, right? And then this is, by the estimate we proved before, this is some constant, and then the LP norm of G, and then Z1 minus Z2 to the 1 over 2 over P, but the LP norm is the same, so then this is C of F P Z1 minus Z2 to the 1 minus 2 over P, like this, which is exactly as claimed. So this is exactly the inequality as claimed, right? Everybody happy? Yeah? Cool. So we have that this estimate gives us that we now are mapping from LP into Holder continuous functions in this way. Okay, cool. All right, so the big advantage of this, as I said, is that we want to have these differential relations, or differential equations, I should say. These are differential equations in terms of weak derivatives as opposed to strong, right? And to do that, we're going to have to start again. We want to write this as weak derivatives as opposed to strong for arbitrary f that are not just smooth. So these relationships are when we have smooth derivatives, right? That's how we prove them. Yeah? We want this for arbitrary functions f, but arbitrary functions f that are in LP. But this kind of estimate will exactly allow us to do that, and that's what we're going to do in the next board. But before we can do this, we've got to try and understand what we mean by weak derivatives. And weak derivatives, we've talked about this already, is when we test with test functions and we can integrate by parts. But these are complex valued functions. There's Werdinger derivatives. So what we're going to show is if we have, say, smooth, so well, it doesn't have to be smooth, it can be Sobolev, but it's enough for our purposes, smooth f and g, then if we do something like this, if we do the conformal part of the gradient times g like this, then this is equal to this. Oops, this should be dz, since we're doing everything in z. And this is like this. This is what we're going to show. So if this was just doing, if we just had one derivative in the real line, then this is trivial, it's integration by parts. This is going to be fairly straightforward, same kind of thing. I should actually say that these are compact supported, smooth functions. But we want to check that there's nothing weird happening, because now we are taking functions that are complex valued. This is complex multiplication, and this is the Werdinger derivative, which outputs a complex number itself, right? So we're going to just verify that this is true, and once we do that, then we'll have a reasonable notion of what it means to have a weak derivative for these guys, because it'll just mean we're testing against a smooth function, and we have the derivative is on the smooth function. Is it clear where this is going? Yeah? Cool. I'm going to raise the board. We want to verify that we can treat weak derivatives in exactly the same way when we have these Werdinger derivatives. So claim that if we do this, df by dz dg, I want to do the double integral dz, this is the same as minus the integral of, let's write f dg by dz. And of course, we expect the same thing to be true, and it is true when we do the anti-conformal part of the gradient. So if we do double integral df by dz bar dg is minus the double integral of f dg by dz bar dz, like this. All right, let's do it. So we're going to write f is equal to f1 plus I of f2, where we're thinking of f1 and f2 as just being in terms of x and y. So actually, let me just write that out. So f of x plus iy is equal to f1 xy plus I f2 xy, and the same for g. Oops. All right, so let's just do the conformal part of the gradient. So we're just going to do this guy here. The other one will follow in exactly the same way. So what we have that d by this equals 1 over 2 d by dx minus I d by dy. Right? That is the Werdinger derivative. And the first claim is as follows. So notice that if we have h, which is from R2 into R and smooth, compact support, and we could show this stuff, df by, dz, h z to minus the integral of f dh by dz, then we would be good, because this thing g is just this function consisting of the real and imaginary parts. So then we can break up this integral into the integral of df dz times g1, right? And then plus I df dz times g2, right? And then if this holds true for arbitrary h, which is smooth real valued, then we can just put back together the relation that we established for g1 and g2, and we'll have exactly this, just by linearity and the rules of complex multiplication. Do you guys believe me on that? Yeah? Makes sense? Then let's call this thing star. Then star would follow. So let's see what happens when we do that. So then if we do this double integral, let's put the half out here, and then we're going to have d by dx minus I d by dy of f1 plus I f2. All of that stuff is multiplied by h, so that's multiplied through 1 over true, or let's do the differentiation through. So let's first differentiate with respect to the x, and we're going to have this f1 comma x plus I f2 comma x, and then let's do this stuff. We're going to have a minus I f2 comma x, and then we're going to have a plus f2 comma y, like this, times h. Yeah? I'm missing out the integration dz, but whatever. Yeah? And let's put the x stuff together, which is this term and this term, and then integrate by parts. So then this will be minus 1 over 2, and we're going to have f comma f1 minus I f2 like this, and then putting the derivative on h, we'll have like this. Cool, thanks. All right, so that is integration with respect to the x. Now let's do with respect to the y. So this is our expression for y. So what we're going to have is, so we've put the minus sign already out there. So then we're going to have plus minus I f1 plus f2 h comma y dz, like this. Yeah? Same thing. We're just integrating by parts with respect to the y variable. We know that we can because things have compact support, and we're all okay. Yeah? All right, let's put together the f1s and the f2s. So minus 1 over 2, and then we're going to have f1, and then it's going to be timed h comma x, and then we have an f1 from here, so then minus I h comma y, like this. Let's put again the f1s. And then the f2s, we're going to have an f2 from here, so h comma y, like this. This is the f2, and then minus I h comma x, like this. Yeah? dz. Yeah? Now let us multiply this and divide it by I. So if we multiply and divide by I, we're going to have a plus I here, and then we're going to divide by I here, like this. Yeah? And then what's that going to give? That is going to give, let's put it over here, minus 1 over 2, double integral f1, h comma x, minus I h comma y, and then plus I f, and we are going to get, all right, so then when we divide this through, then what we're going to get, we're going to have h of comma x, and then this will be minus h comma y, like this. Cool. Z, and then we can just factor out this guy here. Let's put this half through, and then we're going to have minus the double integral of f1 plus I f2, like this, and then here we're going to have, well, what we have here, if we take the half sign out, we're going to have exactly the Werdinger derivative, dh by dz, like this, yeah, dz, and then this is exactly what we want, so this is minus the integral of f dh by dz, dz. Yeah? Cool. So we have indeed this identity, and this identity follows in exactly the same way. Just take some h, integrate by parts, collect up the f1 and the f2, and what will fall out is exactly the Werdinger derivative of, in that case, the anti-conformal part of the derivative with respect to h. Okay, everybody happy? Yeah? So this gives us a way to write things weakly by testing them against initially smooth functions that are of compact support from the complex plane to the complex plane, and the Werdinger derivative behaves exactly like it would do if we were just taking one derivative on the real line. Yeah? So if f belongs to LP, then we have these identities that we want. So if we do d by dz of p of f, we will end up with this thing right here. Okay, let's just say this. And if we do d by dz bar p of f, this is going to be f in the weak sense. And having this in a weak sense will actually say that this function here will be a Sobolev function, that its derivatives will exist in an LP sense. Because we're saying that this derivative weakly is equal to this function, and this derivative is weakly to this function. So that will say that we are in good shape. But what we need is something that we don't have, but we will have later, if the Bernoulli transform from LP to LP is bounded. Okay, if that's the case. Okay, now we know it's bounded when we take L2 to L2. It's actually an isometry, right? We proved this. But now we want this for some p which is bigger than 2, and that's going to be a much harder thing to do. And that's where we're going to invoke the theory of singular integral operators, and we'll talk about this at length. We will actually show bounded with norm CP, where the limit as p goes to 2 of CP is equal to 1. Okay, and that too will be crucial. Okay, so that will come later when we get into single integral operators. But we're going to assume that for the time being, and then the claim is that what we know about this operator P and what we know about, well, this assumption we make on the Bernoulli transform means that we can write this weakly as follows. Okay, why so? How would we prove this? What's the natural way to prove it? What's a natural way to prove this result? Yeah, we have to approximate it by smooth functions. There's no other thing to do, no? So take smooth functions of compact support Fn on the complex plane, which is approximating this in LP, right? F minus Fn LP tends to 0 as n tends to infinity. Okay, so what does it mean? What does this mean weakly? So let's start with this guy. Let's call this guy star. So if we take this thing, this is a perfectly well-defined function. This is what we've established. It's actually a whole continuous function. So if we take this guy and then let's multiply it by some smooth test function like this, where we take the Werdinger conformal part of the gradient with it. Okay, let's take that expression, dz. Now, we know that this thing, so has got compact support, right? So for phi, which is of compact support, we have this expression right here, right? And our claim is that this is equal to the limit as n goes to infinity of this thing. Like this. Because if we consider the difference between these two guys, this is a linear operator, so if we do this, and if we consider the difference, then the difference for any finite n between this thing and this thing, we can write like this, right? Yeah? And then what is this? Well, if we write down what we're actually integrating here, then actually let's put it right here. Then this thing times this thing. Yeah? But this is a function of compact support. So this quantity right here is actually it's bounded, and the integral we're taking this over is going to be finite because this thing has got compact support, right? Yeah. So if we take the norm around this thing, let us put the norm inside, or let's take stuff we don't care about outside. So let's take the supremum norm of the gradient like this, which we don't care about. Like this, it's smooth, but I'm writing an infinity norm. And then we are going to have the double integral of the absolute value of p of f minus p of fn acting on z like this. But now the integral is over the support of the test function like this, which is some finite set because we have finite support, right? Like this, yeah? But then this thing, we know it's less than some constant, the f minus fn LP norm, like this, and then the supremum over compact support test function of z of 1 minus 2 over p. Since we're in compact support, this thing is indeed finite. Right? This thing is indeed finite, and this thing is going to 0. So it goes to 0 as n goes to infinity. Yeah? So this claim is true. Yeah? We pick our test function, if we write it like this, then it's the limit of this expression. Yeah? Everybody happy with that? Thumbs up if you're with me here. Okay, so star is established. It's probably the wrong word. Established. That was proved. And in the same way, we can do this for this guy. We'll get to that in a second. Let's look at the right-hand side here. So if we want this to be true, what would it mean? It would mean that if we consider this thing, if we consider this expression, then the double integral of f this z. So if this was true, this would mean that if we do this integral of this expression, it should be equal to minus this expression. That's what this would mean, right? So this thing should be minus this thing. That would be saying that, in the sense of the weak derivative, this is true. Yeah? Yeah? And we want to understand this expression in terms of approximating sequence Fn. And we claim that this thing is also the case, that this is the limit as n goes to infinity of the double integral of f of fn times phi dz. And this is also easy to see because our assumption is that this thing is a bounded operator with respect to LP, right? And these guys, this is f and LP, and this is fn approximating f and LP. So we can do exactly the same thing. And look at this expression. Let's put it inside the operator fn, like this. And then we can do anything that we want. We could do, for example, we could just use holder. This is of compact support. It is therefore in the holder conjugate space, LP prime. So then this is this. And then this guy is in LP prime. And then this thing goes to 0 because we have a bounded operator in LP. So it's less than some constant f minus fn LP times this thing, LP prime, which goes to 0 as n goes to infinity. Yeah? Yeah. So we have that this guy is equal to this limit. This guy is equal to this limit. Yeah? Let's put those things together on the same board. Because once we look at this thing, then double integral of P of Fn d phi by dz is by integrating by parts. These now we're in the world of things where we can integrate by parts. Because this is a smooth function and this is a smooth function and this output is a whole continuous function, and that's good enough for us for the calculation we just did over there. So we can put this on the other side, sort of minus sign here, d by dc of P of Fn, like this. This is dz, this is dz. And then we use the fact that now we're in this smooth world, we can use the identities that we know. So then this is minus, and then this is just the Berlin transform of Fn. Okay. So then passing to the limit on the left-hand side and the right-hand side, we're going to get the identities we want, because this thing is the limit of this expression. This guy is the limit of this expression, so therefore this thing is equal to this thing. Yeah? Thumbs up if you're with me here. Okay, cool. And then this guy follows in exactly the same way. In fact, a bit easier because we don't need to use boundedness of the Berlin transform. It's exactly the same identity. Yeah? Cool. So then this gives us that we can apply this to any f which is an LP, right? We are now able to apply this stuff to f and LP under same assumptions. We'll have that S of dw by dz bar is equal to just dw by dz for any w belonging to w1p complex plane. The complex plane like this, okay? And that's going to follow in exactly the same way. So it's true whenever we have a smooth function, right? That's the identity we proved. Take any w in w1p. Something I didn't tell you. This thing can be approximated. No, I did tell you. We can approximate a function in w1p with a smooth function in the w1p norm, okay? Which in particular means the gradients will converge in the LP sense. Yeah? And this follows from this convolution type stuff we talked about briefly. So this thing will follow just in exactly the same way that it's true when we take the approximating sequence, and the difference between the approximating sequence and the function is controlled because this guy is LP bounded, you know? And this guy that's just straight away, just by definition of approximating the gradient in LP. Yeah? So we also have this is true from similar arguments. Yeah? Everybody happy with that? Yeah, makes sense. Cool. So we are going to use this to prove the first case of, or the simplest variation of the Beltrami equation. So theorem, suppose phi belongs to LP, complex plane to the complex plane, and measurable mu from some nice region omega into the complex numbers where the absolute value of mu is strictly less than equal to, say, lambda, which is strictly less than 1 almost everywhere. Then we can find f such that the f by dz bar is equal to mu df by dz plus this guy right here. Okay, proof. So out of this, being able to solve this equation for any LP, we will with not too difficult an idea or transformation, be able to solve the Beltrami equation that we're interested in. This is how we're going to start, like this. And we're going to define f as follows. So define f to be this operator p, 1 minus mu of s minus 1 times this thing, like this. Okay, so first we have to discuss why this even makes sense. So why does this make sense? So first observe the following thing. So since we have this y hypothesis that the operator, the Berlin operator, as an LP norm, so let's just write this. So since the LP norm, since CP, the operator, the LP operator norm of S is such that the limit as p goes to 2 of Cp is equal to 1, then we can take it such that when we take the product of mu and this Berlin transform, then that thing will be an operator of norm strictly less than 1. So then we can find p close enough to 2 such that operator say G goes to mu times the Werdinger transform of G has norm less than 1. So what do I mean by this? So if we take G in LP, then S of G is another LP function by hypothesis on the Werdinger transform. And then we just multiply it by this measurable function here, which has got absolute values strictly less than 1 almost everywhere. Yeah? And then I claim that that means that this thing is going to have norm less than 1 because of what? Because, go ahead. We can estimate it. I mean, it's a very big open problem. What is the exact operator norm of the Werdinger transform? And there's a conjecture about it. But we will be able to show this. We will be able to estimate it from above. So we will indeed be able to show this. Yep. Yep. So why is this true? So if we take the LP norm of S of G, then since this is just an L infinity function, right, and it is bounded strictly by lambda, right, so then this is going to be less than, or can you write like this? It's less than this, the L infinity norm of this, and then this, LP, right? You can just take this coefficient out from this integral, yeah, and then this is less than lambda times CP. CP is bigger than 1, but it is as close to 1 as we like, right? It's as close to 1 as we like. And this guy, lambda, is strictly less than 1. So we can take some p such that this thing is strictly less than 1. Yeah? Strictly less than 1. Let's actually call it something, let's say it's less than this thing, which is less than 1. Yeah, in the hypothesis, we do need it to be an LP, but that'll be easy to satisfy. Okay, so if we do that, then we have the following is the case. So consider the operator which goes like this. Let's call it G still. So G, which goes from the sum from k is equal to 1 to infinity, 0 to infinity, 0 to infinity of applying this operator. So we're going to write mu of S, and then I'm going to put it to the power k, and what that means is that we're applying it over and over again. So G, so i.e. the first thing is just doing it with nothing. It's just G, and then the next thing is applying it once. So we're going to have mu of S of G, and then the next thing will be let's break this stuff off. Will be mu of S of mu of S of G, and so on and so on and so on. And the next thing will be mu of S of mu of S of mu of S of G. Okay? That's what I mean by this infinite expression right here. Yeah? And then if we do that, then this thing itself will be a bounded operator because if we take the operator norm of all this stuff, if we take the LP norm of all this stuff, then so this thing, sum k equals 0 to infinity. I want to that makes no difference. I maybe want to do this just for aesthetic reasons, but it makes no difference. P, and what's this? Then that's like applying this thing over and over again, so it's going to be less than LP norm of this thing, and then this thing, so it's going to be less, this thing is going to contribute this W, because the norm of this guy by our choice is less than W, or not W, omega of G of LP, right? So this guy is bounded above by this thing, yeah? And then this guy, it's going to be bounded above by W, by omega times the LP norm of this thing, and the LP norm of this thing is this thing. Yeah? So then the next time will be omega squared GLP, and then so on, like this. Yeah? So it's less than the sum from k equals 0 to infinity of omega to the k G of LP. So this is a bounded operator. Yeah. Cool. And what's more is that we can think of this operator as being the following. Being like this, as being 1 minus mu of S, the minus 1 acting on G. Just by using this standard geometric series stuff that we know from calculus. So we know the sum from k equals 0 to infinity r to the k is equal to 1 over 1 minus r, like this. And the claim is that this being a well-defined operator, you can also think of it as being like this. It's being like this. Okay? And that will give this thing some coherent meaning. Okay? Once we have that, then we are going to apply our various differential relations and show that such an f will satisfy this equation. That's where we're going to go with this. Okay? But we have to be a little bit careful to make sure that we have some reasonable meaning for this, and that's what I'm going to talk about in the next class. Yeah, that's exactly why I need this. Yeah, that's exactly why I need this. Otherwise, I can't define this. This is not a well-defined operator, and we just get nowhere with this. That's true. That's true. That's true. That's true. That's true. No, it does matter. It does matter. The way I formulated this, is not good, because yeah. So this p we choose has to depend on what this lambda is. Yeah, this p we choose has to depend on what this lambda is, and so I should have said the lambda first, and then we can find p sufficiently close to 2, such that if this is true, such that if we have this guy in LP, then we can solve this. So this this formulation is really, really bad, what I just did here. Okay, I think I'm going to have to state that theorem again on Wednesday. But yeah, thank you for pointing it out. Yeah. We're going to apply this for phi, which is like this. Phi of z will be z on omega and then 0 outside. So if omega is a bounded domain, it's inside in every LP space we want. Yeah. It's not a serious restriction, but I should not have stated it this way. All right, that's annoying. All right, thank you anyway. All right, see you.